Again, welcome to Inferential Statistics in Decision Making. These lectures cover conditional probability and the multiplication rule. Our main objective is to learn how to determine conditional probabilities, also distinguish between independent and dependent events. We're also going to use the multiplication rule to find the probability of two events occurring in sequence, and also use the multiplication rule to find conditional probability. So a conditional probability is the probability of an event occurring, given that another event has already occurred. For example, what is the probability that a cigarette smoker may have a lung cancer? So the condition here will be a cigarette smoker. The event that we want to know is the cancer. So this will be the probability of having cancer given that the person smokes a cigarette. So that's our condition, smoking cigarettes. And it's normally denoted as P as probability of event B given A. So the vertical line here will mean given A. So A will be our condition, something that has occurred already, and we want to know if A occurs, B also may occur based on some probability. So this is read as probability of B given A. Now let's see one example here. Two cars are selected in sequence from standard deck. Now standard deck total cars will be 52. Now yes, they say find the probability that the second card is a queen. Now the total number of queens we have is 4. Given that the first card is a king, assuming the king is not replaced. So if a king is already picked, that's our condition. Now, what's the probability that we're going to get a queen? Now here, we know that the total amount of cards are 52. So if king is already selected, then the total amount will be 51. So here we say because the first card is a king and it's not replaced, the remaining deck has 51 cards now instead of 52. And 4 of them are queens. So the probability that our second card is a queen, given that the first card is a king, will be 4 divided by 51, which will give us 0.078. Now let's see a second example. The table shows the result of a study in which a researcher examined a child's IQ and the presence of a specific gene in the child. Here they say we should find the probability that a child has a high IQ, given that the child has the gene. Now we can see from the table here, we have the high IQ and the normal IQ. Now the gene present for the high IQ is 33. The gene is not present, is 19. Total, we have 52. The normal IQ, the gene present is 69. Gene not present is 11. Total is 50. So total altogether is 102. Gene not present, total is 30. Gene present, total is 72. Now the question says we should find the probability that a child has IQ. So a child may have IQ and the total IQ is 52. Given that the child has the gene, so that will fall around here, 33. And the total. So let's see the solution. Here we said there are 72 children because the total for gene present is 72 who have the gene. So the sample space consists of these 72 children. Now, some of them have IQ and some have normal IQ. So of these 33 have the high IQ, 33. So the probability of having a high IQ, given that the gene is present, the total gene is present is 72. So we are going to divide 33 by 72. So that will give us 0.458. Again, probability of high IQ is 33. given that the gene is present, the total gene present is 72. So 33 over 72. Next, let's talk about independent and dependent events. Now, independent events is the occurrence of one of the events does not affect the probability of the occurrence of other events. So that's why we call it independent events. So if we have two events and we say the two events are independent, it means if one event occurs, it doesn't determine if the second event will occur. For example, we'll be rolling a dice. The dice have 6 sides. It doesn't mean if I roll a die and I have 2 sides, there's a chance that next I may have 6 sides or 5 sides. So rolling a die is an independent event. Again, the occurrence of one of the events does not affect the probability of the occurrence of the other event. So here we say probability of B given A is equal to probability of B. Or probability of A given B is equal to probability of A, because here A doesn't determine B. So probability of B given A will be probability of B. Now, if A determine B, as we saw in our previous example, then we have what we call dependent events. So for example, IQ and gene present is dependent events because one may determine the other based on some probability. So events that are not independent are called dependent. So let's see one example here. Deciding whether the events are independent or dependent. Selecting a king from a standard deck A, not replacing it, and then selecting a queen from the deck, which will be B. So here our solution saying that the probability of B given A, because here we say selecting a king from a standard deck A, not replacing it, and then selecting a queen from deck B. So probability of B given A, which is probability of selecting the second card, is a queen, given the first card is a king, is 4 over 51. Now, probability of B is equal to probability of queen, which will give us 4 over 52. So here we say that dependent means the occurrence of A changes the probability of occurrence of B. So here we can see there's a change, 4 over 51 or 4 over 52. Now here also they say we should decide whether the events are independent or dependent. Now tossing a coin and getting a head, which will be A, and then rolling a 6-sided die and obtaining a 6, which is B, probability of B. So here we see again, probability of B given A will be probability of rolling a 6, given that the head on a coin, it will be 1 over 6. Now, what about probability of B by itself? That's rolling a 6 side. It's also 1 over 6. So this means they are independent. A doesn't determine B. The previous example, we said they are dependent because we can see probability of B given A was 4 over 51. Because after I take the first card, the remaining card now is 51. So 4 over 51. But if I didn't take any card, 4 over 52, because total card is 52. So the two results are not the same. So here we say they are dependent. Here we can see that the two-sided probability of B given A is still rolling a 6, given that a head on a coin. We don't toss the coin and the die. They are not one unit together, so they may be separate. We see a 6 side, and only one side, which is 6, will come, so 1 over 6. Here also same thing, I have 6-sided, so it's to divide by 6, and only 1 6, so it's 1 over 6. Now let's go through the multiplication rule. Here we say the multiplication rule for the probability of A and B. So the probability that two events A and B will occur in sequence is probability of A and B equal to probability of A times probability of B given A, or probability of B times probability of A given B, which is here probability of A and B. It can also be probability of A times probability of B. This is only if for independent events, the rule can be simplified as this. If here is dependent, because probability of B given A. So this can be extended for any number of independent variables. So probability of A and B and C. If the three events are independent, then it will be probability of A times probability of B times probability of C. So let's see one example here. Here they say we have two cards which are selected without replacing the first card from a standard deck. Find the probability of selecting a king, then selecting a queen. So here we say because the first card is not replaced, the events are again dependent. We can see probability of K will be 4/52. But probability of Q given K will be 4/51 because we said it's not replaced. Now, if the first card is replaced, then they are going to be dependent because we're going to get 4/52 times 4/52. Again, the question says find the probability of selecting a king, then selecting a king. But the two cards are selected without replacing the first card. So we get 4/52 for the first card, because the total cards are 52. But for the second card, we didn't replace the first card, so we get 4/51. Now, next is using the multiplication rule. So here a coin is tossed, and also a die is rolled. Find the probability of getting a head and then rolling a 6. So here we say the outcome of the coin does not affect the probability of rolling a 6 on a die. So we have two events that are independent. So the probability of getting head, when we toss a coin, we only have two sides. So it will be half, head and tail half. But a die have 6 sides. So probability of getting 6, it will be 1/6. And that will give us 1/12, and roughly it will be 0.083. So the next example here said the probability that a particular nail surgery is successful is 0.85. Find the probability that the 3 nail surgeries are successful. So again, the probability that a particular nail surgery is successful is 0.85. Now we should find the probability that 3 nail surgeries are successful. So what's the solution? We say the probability that each nail surgery is successful is 0.85, which is the first each one. So the chance for success for one surgery is independent of the chances for other surgery. So this means we are going to have all the 3 surgery will be 0.85 times 0.85 times 0.85. So that will give us 0.614. Again, if they are dependent, then their probability values will change. Because the question here again said the probability that a particular knee surgery is successful of 0.85. Now we should find the probability that 3 knee surgeries also are successful. And this will be, and there's no way that we say, okay, if a first surgery is successful, that may determine that the second surgery will be successful or not. We can't. So they are independent, which means the probability for all the 3 surgeries will be 0.85. Now let's find the probability that none of the 3 nail surgeries is successful. So that will be 0.15. Since we know successful is 0.85, not successful will be 1 minus 0.85. So that will give us 0.15. And again, all the three surgeries are independent events. So it will be 0.15 times 0.15 times 0.15. And that will give us 0.003. Now, next is find the probability that at least one of the three main surgery is successful. So here we say at least one, which means it can be one or more. So the complement to the event at least one successful is the event that none are successful. So using the complement rule, we can say probability that at least one is successful will be 1 minus probability that none are successful. Now, probability that none are successful is 0.003. The reason why, because we did a calculation here saying that probability that at least one is successful. Sorry, one more slide down. Yeah, so here we say probability that none of the three surgery is successful. The success is 0.85, so not successful will be 0.15, and there are three, none of them, so that gives us 0.003. So now this means to find the probability that at least one of the three nail surgeries is successful, then we are going to subtract 0.003 from 1 because the three none are successful. Here we want to say at least one, which means all the three can be possible. So that will give us 1 minus 0.003. That gives us 0.997. Now let's look at the next example. They say we should use again multiplication rule to find probabilities. Here we say more than 15,000 US medical school seniors applied to residence program in 2007. Of those, 93% were matched to the residence position. Now, 74% of the seniors matched to a residence position were matched to one of their top two choices. Now, medical students electronically rank the residence program in their order of preference, and also the program directors across the United States do the same. Now, the term match refers to the process where a student's preference list and also the program director preference list overlap, resulting in the placement of a student for a residence position. Now, first they say we should find the probability that a randomly selected senior was matched a resident position, and it was one of the senior's top two choices. So first we have A, which will mean to match to a residence position. B is to match to one of the two top choices. So the probability of A to match to a residence position is 0.93. It's given the question 93% were matched a residence position. Now, probability of B giving A also is given to be 74%, so 0.74. Now, our question says, find the probability that a randomly selected senior was matched to his resident position. We know the probability of matching to a resident position is 93%, which is 0.93. And also, match to one of the two top choice is 0.74. Probability of B giving A. So here we are looking for probability of A and B because we are looking for probability that a random selected senior was matched a resident position and it was one of the senior's top two choices. So we get probability of A and B will give us probability of A times probability of B giving A, which will be 0.93 times 0.74. And that gives us 0.688. Next example, we should find the probability that a randomly selected senior that was matched to a residence position did not get matched with one of the senior top two choices. So here we can find the complement. We know the percentage of, or the probability that the senior was matched to top two choices. So 1 minus that probability will give us not get matched. So let's see the solution. Here again, as we said, we use the complement. So probability of B giving A was I think 74% or so. So probability of not B giving A, which means not match. And so that will be 1 minus 0.74. Because probability of B giving A is given to us. And that gave us 0.26. So that will be the conclusion of these lectures. Again, these lectures we focus more on conditional probability concept and also the multiplication rule. Now, using the multiplication rule, we saw two different formulas. If the events are independent, we multiply all of them, which means one event doesn't determine the other event. Now, if the events are dependent, then this is where we use the conditional probability formula. So again, see you in the next lectures, and thank you for your time. Again, if you have any question, you can send an email through the Blackboard. Okay, thank you.